Hello and welcome. In this video, we are going to calculate series parallel RLC impedance. In this case, since we have both combinations of series and parallel with inductors and capacitors, we need to use our susceptance equations. So that is where we are going to start. We'll break down our R2 and XC section first, and then we will break down XL and R1 together and then combine them together at the end. So we'll start off with that bottom there. So we'll say that our susceptance for that, we can call that YRC. Keep track of each of our variables. And in this case, we have R2. So we'll say that we want the conductance of R2. And we will add that to the XC susceptance, which is BC. And so we know that these are going to result out into YRC equals 1 over R2 plus J 1 over XC. We can solve for each of those. We'll say 1 over R2, which is 2000. Send that out, and then 1 over 430 for our XC. And so those two will be put into millisiemens. So YRC is equal to our 0.5 millisiemens plus J 2.32 millisiemens. So at this point, we can flip this into polar form. That's our square root equation. We'll take our first number of 0.5 and square it, add it to our second number of 2.32 and square it. That gives us our magnitude, YRC in polar form, of 2.37 at an angle of, do our tangent equation next, inverse tangent of our second number, so 2.32 divided by our first number of 0.5, 77.8 degrees, and this is still in millisiemens, so we got to keep that in mind when we do this next stage here, which is getting to our Z value. Our Z of RC is equal to 1 over YRC. So we just need to invert it. So we'll send that out and say 1 over the magnitude that we got, which is 0.00237. That's out of the millisiemens into main Siemens, and that gives us 422. So 422 at an angle of, and we'll flip this phase angle here, so negative 77.8. That is now in ohms. So at this point, we can flip this into rectangular form because we're going to, in the end, need to add this to our other value here. Let me change colors and we'll put in our final rectangular form for this number here. And that requires our cosine and sine equations again. So we'll say 422 cosine of negative 77.8. It says 89. So write that in. So our ZR in rectangular form is equal to 89.2. And we'll do our sine side of this. So 422 sine of negative 77.8 and negative, so minus J 412. And that is now in ohms for both of those values there. So this is important that we have that negative in front because we're talking about the capacitor and the resistor, and the capacitor gives us that negative. So next section, we expect the output, this final Z value for our RL section, to be positive, J. So R1 and XL can be combined together in series, so we'll just place them into our Z equation directly. ZRL is equal to the series of R1 and XL, so we'll just plug those directly into our rectangular form equation. So 2000 plus J 680. Those are both already in ohms, and so that means that they directly match up there. We can combine like terms and solve for our ZT. So that is our final stage here. We'll say that our Z is equal to, and we'll plug that into our triangle equation. 2000. We'll add them up. We'll combine like terms. We'll say that we have 2000 plus 89.2 gives us 2089. And then we will track the other two here. So we've got a 680, a 412, gives us a positive number, so plus J 268. Those are both in ohms. So we can plug that in. That's our answer here for this top one. So 2089, 268. And then we just need to put it in rectangular form. So we'll use our triangle equation now. Say 2089 squared plus 268 squared gives us a z value in polar form of 2106 at an angle of, we'll plug in our tangent equation again. We'll put our second number on top, that's 268 divided by our 2089. Our angle is 7.1 degrees. They want it in kilo ohms, so we'll move our decimal point back 1, 2, 3 spots. 2.11 at an angle of 7.31 degrees. Plug that in. 2.11 and 7.31. Check that. Go. So if you guys have any questions, feel free to reach out.